Hello, and thank you for joining LCGC today for our presentation with IDEX Health and Science, titled Successful UHPLC, Build on the Basics. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's web seminar. The goal of today's discussion is to deliver some practical ideas to help you obtain the best results no matter what chromatography system you're using, but with particular emphasis on fluidics for UHPLC. Every liquid chromatography system incorporates basic components in more or less the same order. But as today's presenter will demonstrate, it's often the connections between the essential components, the pump, the injector, the column, the detector, that can cause or cure some of the most common yet troublesome problems with achieving good chromatography. Our format for today's event will be a brief overview and introduction, followed by the presentation. We've saved time at the end to answer your questions, so you can begin keying those questions anytime in the box on your screen. Today's presenter from IDEX Health and Science is a name you may know through his work on one of the most basic handbooks for any chromatography lab, All About Fittings. John Batts joined Upchurch Scientific in 1996 as its first technical specialist and has worked for that facility, which is now part of IDEX Health and Science, in a variety of capacities over the last 16 years. Currently, John is a senior technical specialist assisting customers with a wide selection and use of products from Upchurch Scientific. He also conducts training sessions on chromatography and commercial excellence across IDEX. John, what are the major concerns you hear from customers who consult with you?
Well, Laura, interestingly, the most common issues that seem to be related to flow path hardware and that often come up in the discussions that I have with UHPLC users are really the same or very similar to the ones that are faced by those who are using regular HPLC. First of all, chromatographers often want to know how to make and how to ensure the good connections in the flow path. I've heard lots of questions like, what's the best fitting that I need to make this connection in my system? Will any fitting work? Are there certain problems that I might encounter? And because the pressure in UHPLC is so high, there's a tremendous amount of stress on the connections, and that makes choosing the right ones critical. Another topic that often comes up during the discussion relates to tubing. And specifically, based on some of the conversations that I've had with chromatographers, they often want to know what is the best tubing for their application. And ironically, because of the way that chromatography is taught at the university level, in many cases, chromatographers simply don't know the impact that tubing can truly have on the final results, on the chromatographic results that are obtained. And then there's this other major piece of the system in this mission-critical area of the system, and I'm talking about in the flow path, anywhere where the sample is present, where pressure is at its highest, and we're talking about typically from the injection valve to the column. That's really that very, very critical area, and expanded out from the outlet of the pump. Of course, there's no sample there, but from the outlet of the pump to the inlet of the detector, that entire area is really a critical zone of the entire system. And in that area, one of the most critical components is the injection valve. So people are oftentimes asking, what are the things that we have to do in order to make sure that the injection valve is running properly? That if there are problems that seem to be coming up, could they be related to the injection valve, and how do I move past that? And in the end, overall, chromatographers, whether they're doing UHPLC or whether they're doing regular HPLC, they all seem to face the same challenges, things like band broadening and carryover and peak splitting. All these are struggles that if you're not already experiencing them, they'll eventually come up if you spend any significant time doing chromatography. And interestingly, while these problems aren't always caused by fittings and tubing and poorly maintained valves, the fact is almost every single major chromatography problem that somebody encounters can be caused by those things. So it's important that you have the right fittings and the right tubing and the right valve that's been properly maintained, because all of those contribute significantly to the overall chromatographic results that you achieve. And that's true in HPLC and even more so in UHPLC. And so those are the things that we'll be focusing on today.
John, with an eye toward addressing those frequent concerns that you hear from your customers, Can you first talk about what's common and what's different between HPLC and UHPLC, aside from the obvious, the high pressure and higher pressure?
Well, that's a good question, and there are a number of things that actually separate UHPLC from HPLC. And while I know it seems to go without saying, the primary difference really is centered around the amount of pressure between those two techniques. And regular HPLC might routinely see pressures that are in the range of somewhere between 1,500 and maybe 3,500 psi. But it's not uncommon for UHPLC pressures to reach 10,000 and 15,000 and sometimes even as high as 20,000 psi with some of the newest systems on the market. So along with that increased pressure that you see in UHPLC, you also see some other differences. You see people that are running at lower flow rates and at the same time demanding higher levels of sensitivity. And that means that the system equipment absolutely must run at peak performance to ensure that baseline stability on the chromatogram that you need to get the results that you're looking for. And in addition to that, you see that sample sizes are often smaller and more analyses are being run on a daily basis, and all of these things add up to higher amounts of stress on the system equipment. Now, along those same lines, because the system pressures are so high and the system stresses are so great, it's important to note that it's easy to reach the functional limit of the performance capabilities of the system equipment. And what I'm talking about is literally the equipment and the materials that are used to manufacture the equipment can reach a functional threshold of capability much more quickly because you're already running at high pressures. And the difficulty is, and the challenge that chromatographers face when they're running UHPLC, is that failures at those pressures can be much more dramatic. And that means you have to pay closer attention to the mechanical stress that's being placed on the fluid pathway. And of course, when you have higher strain on the fluid pathway components, that means that necessarily you have shorter component lifetime. And that means things like fittings and tubing may not always last as long as they have in the past. And because of that, you have to plan for their replacement. And of course, that leads to shorter preventive maintenance cycles. Now, from a design standpoint, there are some noticeable differences as well between UHPLC and HPLC. First of all, because sensitivity is such a primary goal in UHPLC, the fact is that there are truly intentional efforts that are in place to keep the volume in the fluid pathway as small as possible. And that means that the connections are oftentimes very close together, and as Murphy's Law would state, they aren't always that easily accessed. And with regards to the fittings, the most commonly used style of fitting in UHPLC is the traditional all stainless steel connection, and it's just simply swaged onto a piece of stainless steel tubing. And while this fitting system is great at holding tremendous amounts of pressure, it doesn't really work all that wonderfully if you need to move the connection. For instance, if you need to change a column and move from one column to another, and especially if you're changing column manufacturers, that becomes an issue. Now, to help with this, there are some things like some reusable fitting options that are available on the market, but even these have some functional limits regarding how many times that they can be used before they have to be replaced. And of course, the need for sensitivity also impacts the tubing, with the biggest impact on the tubing being the change in the tubing inner diameter. Smaller flow rates and smaller sample sizes require smaller tubing inner diameters. And all of that can lead to higher flow path pressure and a greater likelihood that the tubing is clogged during the run. And just to add a little extra measure of complexity to our lives, sometimes the receiving ports in the system aren't always the same. But even with all these differences, the simple fact remains that flow path connections are one of the most often overlooked contributors to the common challenges that chromatographers face.
Upchurch Scientific very high pressure VHP one-piece reusable fittings changed the game for making connections in UHPLC applications. You'll never again search for a dropped ferrule because the one-piece design assures that the ferrule will stay with the nut. VHP fittings hold to 25,000 psi through at least 10 connection cycles.
So John, is your premise really that many chromatographic problems can be resolved simply by tightening a few fittings?
Well, Laura, it's not really that simple. But the truth is that fittings truly can have a dramatic impact on the quality of your chromatography. And unfortunately, most people who work with UHPLC systems haven't been taught a lot about the hardware connections in the system. In fact, most college classes, they do a great job at teaching the theory of chromatography, how HPLC works and the things that are going on inside the column and the things that govern separation of sample components and all of those things. But generally speaking, they often do a fairly poor job regarding the mechanical operation of a chromatography system. Now, I remember when I first started doing chromatography, and I was working at my first job involving HPLC, my supervisor sat me in a room with a television and a VCR and a stack of VHS tapes. I'm kind of dating myself a little bit, but he said, "Here, John, I want you to watch these videos that will train you how to use the system, and then when you're ready, come on back in the lab and start working on it." And I'm pretty sure that I burned through at least one $2,000 column and likely wasted lots of hours trying to fix leaks and other fluidic issues that were in the system simply because I had no practical, hands-on training how to make good connections in my system. Now, because there typically isn't that level of practical hands-on training, that means that really a lot of chromatographers aren't really all that particularly comfortable with fluid pathway hardware. Now, if you're trying to make connections with something that you're not really that comfortable with, that tends to lead to less than ideal connections. And if you don't have a good connection, that can lead to things like band broadening and carryover and split peaks and missing sample and all of those common challenges. The reality that most chromatographers don't realize is how much a good connection, or conversely a bad connection, can impact the final results, that chromatogram, that chromatographic results that you're looking for. And to make matters worse, it's pretty common for system components to end up being blamed for problems rather than the connections. In other words, what I'm really trying to say is that every major chromatographic problem, while not necessarily linked to the system hardware, to the fittings and the tubing, it can be linked to those bad connections. Now, before I forget, let me simply highlight something, and that is that there's a free downloadable resource that can be found on the IDEX Health and Science website. You can go to www.idex-hs.com, and it's our All About Fittings booklet. The booklet is a 64-page primer on the proper use of fittings in chromatography systems, and that booklet dives much deeper into how fittings work and how they're described and how you determine what the best fitting is for your system and where to use what fitting in what area of the system. And if you get a chance, I'd encourage you. It's a free download in PDF format, so I'd encourage you to do that. Now today, while we can't get as deep into how fittings work as the booklet might go, in order to help explain how fittings can contribute to the most common chromatographic challenges, I'd like to highlight some of the critical features of fittings that often get overlooked. First, as you can see on the slide, when it comes to fittings, there are some common features that most fittings use throughout that critical area of the system. Now, let me redefine that again. What I'm talking about is from the outlet of the pump really to the outlet of the detector. Even though that entire area of the system isn't really under the super high pressure that you might experience in UHPLC, fortunately, they almost always use the same type of configuration. And the things that are the same about these things are for instance, the threads. The threads are 1032 threads. And that may not mean anything to you, and we go into that a little bit in how you describe a fitting and what the threads mean in the All About Fittings guide. But just suffice it to say that that is a term that's used by equipment manufacturers and used by fitting suppliers like our company. And fortunately, most of the high-pressure fittings, or most of the fittings in that critical zone of the system, are using that particular thread. The internal port geometry is typically coned, just like it shows, and the fittings and the receiving ports are typically designed for 1/16 inch outside diameter tubing. And like I said, that's great news, because really what that means is that you could, if you wanted to, use the same style of fitting to connect almost all of your tubing connections throughout the system. But there are some non-universal features of receiving ports. And specifically, the thing that changes the most is the overall depth of the tubing pocket. And this is the portion of the receiving port into which the tubing extends beyond the end of the ferrule, so the ferrule has something to grab a hold of. And because that overall depth of the tubing pocket changes, what that means is that the tubing that extends beyond the end of the ferrule can also vary in length, even from the same manufacturer, because of stack-up of tolerances inside a receiving port. And so that means that when the tubing is extending beyond on the end of the ferrule, and it's varying in length, then that can lead to poor connections. And that's really, really important, especially when permanent swage connections are being used. Because swage connections lock in that length of tubing, and that can lead to a lot of the chromatographic problems that people often face. So let's take a look for just a moment at one common scenario. And this is when the receiving port has a tubing pocket that's really too short for the length of the tubing extending past a swaged ferrule. Now, this is something that's pretty commonly encountered, in fact, when you're changing columns from one manufacturer to another. In this case, the tubing hits the bottom of the receiving port before the ferrule can contact the cone surface inside the receiving port. Now, if this is a traditional fitting system, then the problems that can be created are, fortunately, as far as problems go, are pretty easily seen. In fact, the most obvious symptom that you see from a connection like this is a leaking connection, because there's no seal that's taking place between the ferrule and the cone of the receiving port. But sometimes leaking connections aren't all that particularly easy to spot. It could be because the flow rates that you're running are really low, or perhaps you're running with a volatile solvent that's evaporating more quickly than you can spot it leaking. It could be that the fitting that's leaking is in a difficult to reach area, or in a place in the system that's somewhat hidden from regular view. When that kind of thing happens, that's when you need to start looking for other evidence that a leaking connection is taking place. Things like a drop in system back pressure, or perhaps evidence that the sample that you injected doesn't seem to be showing up on the chromatogram. There's no evidence that anything's moving through the detector at all. And if you're using buffered solutions, sometimes there might even be some evidence of salt crystals that are forming around the receiving port. These are all hints that there's something wrong with at least one of the connections in the fluid pathway. Now, if you look at the opposite scenario, where the tube is too short for the receiving port tubing pocket, this is a much bigger problem. Not just because of all the problems that are created, but also because primarily you can't see the problem. You can't physically see that there's dead volume being created. As you can see from the picture on the slide, the biggest problem in a connection like this is that mixing chamber, that red zone in the connection. That mixing chamber really becomes dead volume in the receiving port, volume that's added into your fluid pathway that the sample has to necessarily touch, especially if it's anywhere from the injection valve to the outlet of the column and even to the inlet of the detector. Any of those connections that are made throughout that region, if there's a mixing chamber that's present, that becomes dead volume that can cause pretty significant problems. And like I mentioned, because you can't see the dead volume, that means you can't physically see that the connection is bad. It's not leaking. The system is pressured up. You're getting something through the detector. All of those things are going on. You're just not getting what you're looking for. And that's when major system components like the valve or the column start to get blamed for problems that really have absolutely nothing to do with them, but instead simply have to do with a bad connection. So, in order to help overcome this problem, in order to at least rule out some of the issues with fittings, here's some tips. First of all, if you're using a swage fitting, realize most often those fittings they're pretty often universal, but only before they've been swaged. After they've been swaged, they really should only be used in the receiving port into which they were originally swaged. That's because that nut and that ferrule, especially that ferrule has been locked in on the tube at the point where the ferrule met the receiving port cone, and the tube being pressed all the way down to the bottom of that specific port. So that length of tubing beyond the end of the ferrule and the ferrule's compression point, all of that is now mated to that one receiving port. So stainless steel swage fittings, universal up front, prior to being swaged, but really very, very specific to a single port after they've been swaged. Another tip is in order to help expand the functionality of the connections that you might have, you can use some reusable fittings, and there are some that are available. And in fact, some of the ones that are on the market, even for UHPLC, are really designed not to permanently attach to the tubing, so that allows the tubing to adjust to whatever the tubing pocket depth is in the receiving port into which you're connecting it. However, it's important to note that just because a fitting is reusable doesn't mean that it will last forever. If you're using these kinds of fittings, you should plan on changing them per the manufacturer's recommendations or whatever input you might get from a service engineer or by calling someone and getting some advice who has experience with using those fittings. And when in doubt, just replace the fittings. If you've tried to make the connections work, you've tried to adjust things, and things just don't seem to be functional, one of the best things that you can do, and often one of the least expensive things that you can do, is just simply replace the fittings. Like I said, they're one of the least expensive things. They're usually easy to access. And if you do so, and you give your system that kind of makeover when it comes to the fittings and the connections throughout the system, it often results in restoring good system performance.
New Upchurch Scientific PEAK-lined stainless steel tubing, also known as PLS, combines the mechanical strength of stainless steel with a fully inert, metal-free flow path of biocompatible PEAK polymer. Each piece of bendable PLS tubing comes with Upchurch Scientific VHP fittings and incorporates a permanent label to identify the length and the inner diameter.
John, so far you've talked mainly about fittings. How does tubing affect the quality of chromatographic separations?
Well, Laura, honestly, like fittings, tubing really can have a huge impact on the results that you achieve in chromatography. And while many chromatographers often, in reality, don't give tubing much thought, there are some key features of tubing that really must be considered if you want to ensure the best results possible. One of the first things that you have to think about is the material from which the tubing is made, because the material impacts both the maximum pressure that the system can attain, as well as the compatibility with the mobile phase and the sample being analyzed. Now, there are numerous options that are available in chromatography, and four of the most popular ones, or four ones that you might consider, are things that, like PEAK tubing, for instance. PEAK tubing, it's great for flexibility. It's great for its ease of use and chemical inertness, and it's been well accepted and well characterized in chromatography. However, even with the smallest inner diameter, it can only be used up to 10,000 psi, and that's, again, only for the smallest inner diameter. Most of the sizes of PEAK tubing can only handle up to 7,000 psi. And that means for many UHPLC applications, PEAK tubing simply cannot be used, especially in that high pressure area from the outlet of the pump to the inlet of the column. Now, mind you, understand, and sometimes it doesn't click with people who are running the system. Just because the system is running at super high pressures doesn't mean that pressure is everywhere in the system. The biggest contributor to system pressure is the column. And, of course, how much resistance the column is providing to the fluid that you're flowing through at the rate that you're flowing and all of those things. So the thing is, though, to understand that when you consider the tubing that you're using, after the column is an area where technically is outside of most of the system pressure you will encounter. There might be a few hundred psi there, but typically you don't see a huge amount of pressure after the column. So you can use PEAK post-column, but pre-column between the pump and the inlet of the column in UHPLC, as wonderful as PEAK is, it's limited in its ability to hold pressure, so typically can't be used. Then there's PEAK seal tubing. Now, PEAK seal tubing it's a fairly popular option and can typically handle higher pressures than PEAK tubing in similar sizes. But there are some limitations as well, especially for those applications where pressures are maybe hitting 15,000 psi and higher. And the other thing to keep in mind about PEAK seal is that there's technically there's fused silica at the core. And so that means that the tubing has a different chemical compatibility than PEEK or than stainless steel or other options that are available, and you just simply have to consider it before you deploy that tubing for use in the system. Another option is stainless steel tubing. Now, stainless steel tubing is a standard that's used throughout a lot of HPLC systems and even UHPLC. In fact, it's really the standard for most of the connections in large part because of its ability to handle the pressure and its compatibility with most of the fluids that are used in chromatography and its ability to bend as needed to fit a particular configuration in the system. But there are some inherent limitations in stainless steel, one of them that a lot of people don't really think about and may not even know about. That's the rough internal surface of stainless steel tubing. Stainless steel tubing is a drawn material. The most commonly used tubing that's used in almost every application where stainless steel tubing is used is seamless 316 stainless. And that's a drawn material because it's literally pulled from a larger size to a smaller size. That causes the inner wall of the tubing to be rough. And because the inner wall of the tubing is rough, there are little nooks and crannies for the sample to hang out, and you can create extra turbulence and extra back pressure. And there's all kinds of little nuances that come with using small bore, seamless stainless steel tubing. And, of course, there's some incompatibility between stainless steel and maybe some sample components like proteins and other similar biological samples that you might want to analyze. Now, the latest entry into the market is this, or at least one of them, is this PEEK line stainless steel tubing that we've introduced. And it combines that chemical inertness of PEEK with the strength of stainless steel, so you truly can have biocompatible or inert UHPLC applications. And you can run those, and it's fine up to 15,000 psi, but there still are some inherent limitations with this tubing. And specifically, it must be only used with reusable fittings. You can't use the normal stainless steel all stainless compression fittings with PEEK line stainless. You have to use reusable fittings with it, and it only comes in pre-prepared lengths. So I guess the big message when it comes to the tubing material is that there are lots of options that are available, and you have to balance the pros and the cons and choose the right one for your application. But it's not just the material that comes into play. As you can see from this slide, there are two other things that can influence the impact of tubing on chromatography. One of those two is length. Now, if you look at the formula that's here, the formula that's shown on this slide is a formula that relates the pressure drop across the tube to several different factors. And this is actually fairly accurate, fairly predictive of what kind of pressure you might expect. And if you look at it, if you're a math person, you can see that there's a linear relationship between the pressure of a tube and the flow rate that you might run, the viscosity of the fluid, and the length of the tubing. And when it comes to the tubing itself, then this can inherently tell you that if I need to minimize the impact of tubing on the overall system pressure, then I want to keep it as short as I can. The shorter the length, the less the back pressure that would come from that tube in comparison to a longer length of the same. And that seems inherently obvious, but it's nice that there's a linear relationship. But I also want you to notice that there's an inverse relationship between the pressure along a tube and the diameter of that same tube taken to the fourth power. Now, what does that mean from a practical and an experiential vantage point? And that is simply this. Even small changes to the inner diameter of my tubing pathway can result in absolutely monster changes, huge differences in the amount of back pressure that's created by that tubing. So there's an example at the bottom of the slide. If you consider an application where you might be running at 100 microliters a minute, and from the outlet of the pump to the inlet of the detector and that pathway all the way through the system, you might have 60 centimeters of tubing, maybe a couple of feet of tubing. And that doesn't seem to be too awful much. It might be a little high, but it's a pretty good amount to make all of the connections through all of the system hardware. If that tubing was at 50 microns in inner diameter, that tubing would only contribute at 100 microliters a minute of just water, a little less than 1,000 psi. But if I take that same tube and over its entire length drop the inner diameter down to 25 micron, And as you can see, by the formula, I automatically create more pressure than many UHPLC systems on the market can even handle, and that's before the column is even present in the fluid pathway. That's just from the tubing. So I share this with you because while it's true, generally speaking, just from good chromatography, that if you can use a smaller inner diameter of tubing, that's great. You keep the zone of interference between the sample slug and the sample components in the mobile phase down to a minimum. And you reduce the volume of the tube so that makes the sample get from the valve to the column more quickly and from the column to the detector more quickly, and that just generally improves resolution and all of those things. So that's just good standard chromatographic practice. But the rule of thumb is don't just use the smallest ID. Use the smallest inner diameter that's functionally possible. You have to consider both the positive and the negative effects that a small tubing inner diameter can have on the system performance. Now, one of the last things to consider is how the tubing has been prepared. Now, as you can see from the photos that are on this slide, there is a difference in the quality of the end of the tubing based on how it's been prepared. And notice that the middle one, of course, is kind of old school. People have just a long length of tubing, don't know how to cut it, so they use a hacksaw or a file or something just to try to cut it off. And while that might get you the length of tubing that you want, if you look at it closely, you can see that there are a lot of problems on the end of that tubing. Now, if you look on the left-hand side, you see this is a commercially available tubing cutter that you might have in your laboratory, and that's fine. It does an average job and provides you with a decent cut. But anytime that you have imperfections on that flat face of the tubing, whether it's at an angle or whether there are burrs and things that are lifting up the edge or whether there are chamfers leading into the through hole, any of those things that are present on the end of the tubing opens up an opportunity for a dead volume pocket to form. And any time that there's dead volume, that opens up more opportunity for the sample and the sample components to mix with mobile phase and therefore dilute out, and then you start losing resolution and the sample components start coming together. You might get band broadening and even carryover depending on how significant it is. And you notice from the picture that's on the right-hand side, the pre-cut tubing that comes from a supplier, that tubing generally is nice and very flat-faced, almost perfectly flat, with virtually no surface imperfections that are there. So when you use pre-cut tubing, there's less opportunity for dead volume chambers to form at the bottom of the receiving port. And when you do that, when you have a good surface on the bottom of the tube that's mated well with the bottom of the receiving port, that means you're beginning to lay the foundation for quality chromatographic results.
Capable of system performance to 15,000 psi, the Reodyne MXT actuated standalone valve integrates seamlessly into any UHPLC system. The MXT offers a 7-port selection configuration or a choice of 6-port or 10-port switching configurations for maximum lab flexibility. Genuine Reodyne valve accessories enable fast, efficient valve maintenance on site.
As we talked about at the beginning of the webinar today, in addition to fittings and tubing, one of the most critical portions of that mission critical area of the system where the sample is present, in that fluid pathway is the injection valve itself. Now in HPLC, it's still pretty common to see both automated and manual injection valves in use, but in UHPLC, the injection valve is most often integrated into an autosampler unless you're using something as an accessory to an existing system that you have. But regardless of the type of valve that your system is using, there are some pretty standard troubleshooting and preventative maintenance suggestions that you can follow to help you get the best performance from your valve and then, of course, the best results from your system. And we're going to highlight some of those best practices and some things to look for, but I also wanted to highlight the fact that we have this resource that's called the Reodyne Troubleshooting Guide. It's also available from our website, again, www.idex-hs.com. It's a free download, and it's really a great resource that's full of practical advice and a lot of very useful and helpful tips for troubleshooting valve issues, things that you might encounter, and how to overcome those problems as you're looking at your Reodyne valve.
John, what happens in the valve that can contribute to chromatographic problems?
Well, Laura, there are actually several things that you need to take into account regarding the injection valve and its overall impact on the results that you achieve. Well, first of all, you need to pay attention to the physical composition of the valve's fluid pathway. It's important to take some time and ask yourself questions like, what truly are the materials of contact? What are the materials of which my valve was manufactured, and are those materials going to come in contact with my mobile phase and with my sample? And if they do, are they compatible with one another? You also need to consider the dimensions of the fluid pathway through the valve. And oftentimes in UHPLC, the fluid pathways, as we've already talked about, are very small. Really, it's an intentional effort to reduce the opportunity for sample components to disperse in the mobile phase. So you keep things as concentrated as possible, and therefore you keep it as you keep the resolution as great as you possibly can by minimizing how much dispersion takes place. Now, while that's good for chromatographic results, it does also make it easier for the fluid passages to get clogged by particulates that originate from the sample or from breakdown of the system components. So if your analyses are prone to generating particles, you have to be careful that you protect the valve accordingly simply because there are small fluid passages inside. Another thing to think about is the actual plumbing. Sometimes just the tubing that you use can contribute to problems that you achieve, and you have to think about, where's my waste tubing and my vent tubing, and how are things coming in, and am I doing the injection process correctly? Is the inside diameter of my tubing, is that appropriate for use with the type of injections that I'm doing? All sorts of things that you have to think about just with the plumbing. But the most popular problem, or most of the problems in reality that can happen with an injection valve, can truly be attributed to those two main components that you see on the slide, and that's the stator and the rotor seal. The biggest problem that you can achieve has to do with those two components, that stator, that rotor seal, and primarily having to do with rotor seal wear. As we'll see on the next slide, the slide helps illustrate what can happen when a typical polymer rotor seal wears over its useful lifetime. Now, the first picture that you see on the left-hand side is an unused surface. It's the surface of an unused rotor seal. The dotted lines that you see in the picture indicate that primary area of contact that will occur between the seal, between the top surface of the rotor seal, and the underside of the stator. So it's really in that area that you'll encounter the most amount of friction. So keep in mind that the rotor seal is most often some sort of polymer material that is really under a huge amount of load. It has small passages, and it undergoes a lot of friction with every single actuation. So when you combine the huge amount of load that's being placed on the rotor seal, and specifically in that zone between the rotor seal and the underside of the stator, trying to hold those surfaces together, and you couple that with the friction of moving back and forth, the end result is wear and tear on the polymer surface. And that's the sealing surface that's beginning to start to wear and ultimately can become damaged over time. So you see, after using that same rotor seal in an application where I have 5,000 cycles, 5,000 actuations, the fluid seal, it's still okay. You might see some small little tears, some little pits on the edges of the grooves that are on the rotor seal, and you also see this very shiny surface that's in the middle, and that's the part, again, that's undergoing most of the contact with the underside of the stator, where you're getting the most amount of load and the most amount of friction. Now, other than the small little imperfections that you see there isn't a lot of wear, and this kind of a seal, after only 5,000 cycles, will continue to perform just fine. Now you move over to the next one. After 30,000 cycles, what you start to see is some more defined wear. That zone, that shiny surface is beginning to expand a bit, and you're seeing more pronounced indentation on the surface of the rotor seal, and there's some damage that begins to occur to the rotor seal around the outer edge. You can see some pitting that's starting to occur as more of that outer edge starts to come in more contact with the underside of the stator. And then at 60,000 cycles, when I've gone beyond the lifetime, the real functional, usable lifetime of my rotor seal, you can see that the seal has really truly begun to break down. And I no longer have a defined shiny section in the middle. It's expanded out to the entire seal because more of that seal, it's becoming more compressed and therefore allowing it to come in contact with the underside of the stator. I'm starting to really pull away material, so you can see divots and pits and things that are on the surface of the rotor seal. The grooves themselves are misshapen. They're smaller. They might even be a little longer but thinner, and you even see some bridging effect between a couple of the grooves, and all of these things can lead to leaking. It can lead to loss of sample, dead volume, and ultimately they can contribute to all of those standard chromatographic problems that you encounter, like the leaking, the band broadening, the carryover, and all of those things that tend to drive chromatographers crazy. And those things can happen just simply because of the lifetime of the rotor seal. Now, if you want to keep your injection valve in good operating health, there are some tips that you can follow. First of all, one of the basic things that you can do is simply monitor the system back pressure. Now, if you start to see some irregularities occurring chromatographically, watch to see if there's a pressure spike that is coincident with the switching of the valve. If there is, that might be a little clue, a little indication to you that there's some damage that's beginning to occur internally. It might be a blockage of a port. It might be some problem with the rotor seal that hasn't manifested as a leak yet, but you can start to see there might be a little bit of problem there that you need to be watching for, and that should be just a clue, a little flag for you to schedule a preventive maintenance. Speaking of preventative maintenance, it's important that you establish a preventative maintenance or a PM schedule. Now, in order to do that, you might need to work with the valve manufacturer or even the manufacturer of your chromatography system to get their best recommendation for the number of actuations that your valve and your system should do, the number of analyses that your system should do in between maintenance cycles. But understand, regardless of what that number is, it's always a better idea to schedule the downtime of your system for preventative maintenance than wait for your system to break down. In the application or the pictures that we saw previously, once you get past that 30,000, you get up to 40,000 and 50,000 cycles, you realize that if I'm successfully running at that, it probably would have been a much better thing to schedule the preventive maintenance at around that 40 and 50,000 cycle range before I got to the 60,000 cycles that caused my seal to really break down. So it's always better to just schedule it. Let your colleagues know that the system's going to be down. It doesn't usually take that particularly long in order to do a preventative maintenance on the valve especially. And you can get the system down, get things changed over, get it back up and running, re-qualified for your application, and likely be running samples and analyzing samples before lunchtime. So if you just schedule that system preventive maintenance, that's always a good idea. And when you take the valve apart, inspect the top surface of the rotor seal like we saw in the pictures previously and the underside of the stator. What you're looking for are little grooves, irregular grooves, not the ones that are supposed to be there, but little grooves that seem like scratches almost, maybe some evidence of missing material that's been pulled away from the polymer surface, just little patterns of damage that oftentimes occur as the surfaces start to wear. And if there's a thing that you notice that seems to be out of the ordinary and you're in doubt, just replace the component with a new one from the manufacturer. Now keep in mind, one of the nice things, especially if it's a reiodine valve that your system is using, it's almost always safe to clean both the stator and the rotor seal. And when I used to do preventive maintenance on HPLC systems a number of years ago, what I oftentimes would do would I'd take the valve apart and I'd take both the stator and the rotor seal and I'd place it into a beaker with some water in it, and I'd place that beaker into a sonicating bath. And I might, while it's in the sonicating bath, I might let it sit there at an elevated temperature for 20 to 30 minutes. And this helps remove any material that might precipitate if it gets exposed to some kind of organic solution. So again, do water first, especially if you're running with buffers or with sample components that might be causing a problem. if it gets exposed to just pure methanol or something like that, if you sonicate first in water, that just removes those things so that you get a clean surface. And then secondarily, after I sonicate in water, what I would next do is sonicate both the rotor seal and the stator in either methanol or isopropanol, and I'd let that sit in a beaker and put that in a sonicating bath again for another 20 to 30 minutes. And that tends to remove any organic contaminants that might be there, as well as any fingerprints that you might have introduced to the surfaces when you were disassembling the valve. Then I would remove those components and put them on like a Kim wipe or some laboratory cloth, something that's lint-free on which they can air dry. And then I would inspect those sealing surfaces. Look at the underside of the stator. Look for any scratches, any marks that might be present that are indicating that there's some wear. More importantly, look at the top surface of the rotor seal and see if there's anything there, any imperfections, especially anything that might bridge between two of the grooves. If it looks irregular, it probably is. And it's at least worth asking the question, is this okay, or do I need to change it out? So I'd inspect those sealing surfaces, and if those sealing surfaces are okay and no problems are found, then I'd go ahead and reassemble the valve and then test to make sure that it's functioning properly. But if not, if there's problems I see, or if I put it back together again and it's still giving me a problem, then it's okay to replace those components with genuine replacement items. And in fact, speaking of that, understand that there will come a time when you will absolutely have to replace the rotor seal. And in fact, given enough time in the system, you may even have to replace the stator. Just the way it is. They're technically consumable items. That's where the highest amount of stress is being realized, and the highest amount of friction, the highest amount of load, and one of those for sure is almost always made up of polymer material. And when you do this, when you have to replace with a rotor seal or have to replace the stator, it's almost always best to just simply use the genuine replacement parts from the valve manufacturer or from the system manufacturer. That's almost always the best thing to do. I recommend that because those genuine replacement parts have been tested for optimal performance for that required surface finish. And whether it's through the equipment manufacturer or through us directly, a good place to start is the rebuild kit. A rebuild kit will almost always contain just the components that you need that are most often wearing on your valve. And those are usually available when you buy them that way at a more attractive price than buying the individual components separately. Now, in addition to these troubleshooting tips, there are a number of other resources that are available on our website and things that might be helpful to you as you go through your system, choosing the right components and making sure that you're doing things properly as a chromatographer. First of all, there's a downloadable version of our catalog that you can find there. There's often also a lot of information about the polymers and other materials that we use. So if you're looking for information about density or looking for information about chemical compatibility or about other physical properties of the materials, all of those things are there. There are standard port drawings if you'd like to design a port to go with our products, helpful conversion tools, application notes, blog posts that you can read and respond to. And again, as we've mentioned, the All About Fittings Guide, the Reodyne Troubleshooting Guide. There's an idea book that's helpful as a resource for OEM manufacturers, and there's a lot of other resources. And in addition to that, on our website, you can also view archived recordings of the past webinars that we've done. And all in all, really, our website isn't just designed to be a portal for purchasing our products. We've tried to design it in such a way, and it's not perfect, but we've tried to design it in such a way that there's a focus on providing as much technical information that we can on the products that we manufacture.
Upchurch Scientific very high-pressure filters, available as inline and pre-column configurations in porosities of 0.2 and 0.5 microns, protect the life of expensive columns and even more expensive UHPLC systems. Each filter system comes with 5 replaceable frit assemblies, and replacement frits are available separately.
In just a few minutes, our expert from IDEX Health and Science, John Batts, will answer the questions you've sent in. So if you haven't keyed in your question yet into the box, now's a good time to do that. John, how would you summarize the high points of today's discussion, and what are some best practices for chromatography labs?
Well, Laura, the first thing that I would do is simply check the connections. Like I talked about, it's important to make sure that all the connections in the fluid pathway are simply just made properly. Make sure you're using the appropriate reusable fittings in areas where you intend to make and break the connection a lot. So if you know that your system is going to have to change the column frequently, well, use a reusable fitting there rather than a permanently swaged connection. And if there's any doubt in the quality of the connection, simply start over with fresh connections that are designed for UHPLC conditions. As I mentioned also, if you're using swage connections, remember, once a fitting is swaged, it should only truly be used in that port into which it was originally swaged. If you're using reusable connections, remember that just because they're reusable doesn't mean that you can use them forever. You need to plan for eventual replacement of those fittings based upon how much pressure they need to hold and the conditions that they're exposed to. Gauge it for yourself, and then once you get used to the normal replacement cycle, replace them as needed. Plan for that. Have those things on hand. When it comes to your flow path tubing, remember to keep your tubing lengths short and, perhaps even more importantly, the inner diameter as small as functionally possible. Remember to use tubing that's been prepared properly and manufactured from a material that's compatible with your analysis. And lastly, with regards to your injection valve, it's always a good idea to simply perform regular preventative maintenance. Scheduling the system downtime will almost always result in less of a headache than waiting for the system to break down and end up with bad results or missing sample analyses that you were expecting. The ultimate goal, ideally, is just simply taking the necessary steps to ensure that your fluid pathway is healthy. When you do that, it will help you achieve great chromatographic results.
Thanks, John. It's now time for our audience questions, and we thank all of you who have already sent in questions. Okay, first one. John, how critical is dispersion in UHPLC, and what pitfalls does it pose for system design?
Well, dispersion in UHPLC is a very important deal. It's a very important problem that can occur, especially as we've talked about when you're dealing with internal diameters of tubing and overall connections in the system. You really have to be sure that you're removing the dead volume from the receiving ports and removing any extraneous volume that you possibly can. So dispersion in UHPLC, it really isn't. If you compare that to HPLC, probably the biggest thing that you have to be concerned about is that dispersion can have a more dramatic effect because sample sizes are smaller and flow rates are smaller. And so if you have the same, like if you use the same tubing for normal HPLC analyses that you might use for UHPLC, if you don't change anything, then and you then reduce the sample size and you change the flow rate, then any dispersion that occurs can only get magnified, and that just tends to cause problems with resolution and the peaks splitting apart, the peaks splitting themselves, and you get carryover effects and all of those things that we've been talking about. So really, ideally, if you have dispersion in UHPLC, and if you're concerned about that, one of the best ways to take care of that is simply those things that we've talked about today, making sure that you're making good connections, that the tubing's pressed all the way down to the bottom of the port when you're making that connection, that if it's a swage connection, it's only used in that particular port. And probably, again, as I'd highlighted earlier, one of the most critical aspects of the fluid pathway that you really have to be concerned about is the tubing inner diameter. Most of the time, people don't even give it a second thought. There's a piece of tubing, it's in my drawer, it looks like it will make the connection, hey, let's go with that. And without really noticing the that internal diameter of the tubing, you can have a dramatic impact on the amount of dispersion because you're adding extra volume. And anytime that inner diameter, we talked about previously what happens if you go smaller. If the tubing inside diameter goes larger, what that does, it does two things that hurt you. One of them is it increases the volume inside the tube, and that means that it takes longer for your sample to move from the valve to the column, or to move from the column to the detector. Anytime that the volume is larger, I have a static flow rate, so it just simply by default takes longer. But perhaps an even bigger problem is that by increasing the diameter, that allows more of my sample proportionally to be an exposure to the mobile phase. And in that zone of interaction between the sample slug and the mobile phase as it leads from the injection valve to the column, and then between the separated components and the mobile phase as it leaves the column heading to the detector. If that zone of interaction is big, that allows for the sample to dilute. And the more diluted the sample is when it either hits your column or when it leaves the column, the more band broadening you can expect, and that loses resolution. That causes what appears to be the components to come closer together, and it's more difficult to do the analysis that you're looking for. So dispersion is critical, and again, more so because you're running with typically smaller flow rates and smaller sample sizes, and everything is heightened whenever you're dealing with UHPLC over standard HPLC. But good standard chromatographic practices, again, keep those tubing inner diameters as small as functionally possible.
John, what changes to system configuration can be made to reduce tubing runs from component to component?
Yeah, that's a great question. Sometimes you can't really change the system configuration very much. And sometimes it's pretty locked in simply because the components are stacked together. The system is already pre-wired as a pre-hardware connection that's there, and it's designed to function in a particular way. So rather than cutting down on tubing links that you might have between components, the bigger impact, as we've highlighted, is tubing inner diameter. But another thing to keep in mind, too, sometimes systems come with things like column heaters and column switching capabilities and those types of things. And if you really don't need that functionality, it's probably good to talk to the equipment manufacturer to find out how can you bypass that, and if bypassing that will cause any problems on the analyses. If you can do that without causing any difficulties, then simply by bypassing that whole column heating block and the column switching area will allow you to get just a short length of tubing to go directly from the injection valve directly into the column, or maybe directly into a pre-column filter and then into the column, rather than going through all of that other network of fluid connections that you have in the column heater. So by doing that can shorten the tubing length for sure and give you ultimately better chromatography if you're dealing with small sample sizes. But aside from that, it's difficult to make any significant changes to the system configuration simply because they're almost always automated systems that are pre-wired.
Great. We have time for probably just one more quick question. Is there a practical way to achieve pre-cut cutting quality in the lab?
Wow, that's a good question too, and I'd say it's tough, especially if you're dealing with UHPLC, because the tubing that's being used, let's say you're using stainless steel tubing. When we manufacture tubing in our facility, it's a very large machine that's kept in its own room. It's an electrochemical cutting machine, and it's a very large, expensive device that we use in order to prepare our tubing. And there just simply aren't those kind of devices that can be used in a laboratory. So if you're using stainless steel tubing, it's a tough job. There are I think a couple of commercially available tools that you can use for your benchtop, but they're not the best option. Again, as you looked at, maybe if you remember those pictures from that slide, the one that was on the left-hand side was made from a tool that was like that. It does an okay job, but depending on the flow rates that you're running, that could be problematic, and you have to be kind of careful about that. So, and then if you're dealing with tubing like PeakSil or the PeakLine stainless steel tubing that are also other options to consider, neither of those options can be trimmed in the laboratory. There isn't any way to do that. They have to come pre-prepared. So there isn't really a practical way to do that, at least not, and get the best chromatographic results possible.
Okay, I'm going to give you one last quick question. Can you explain the term swaged?
Oh, yeah, that's a great question. So when I'm swaging a ferrule onto a tube, what I'm talking about is I'm permanently attaching. So if I put my nut over the tube and I place my ferrule over the tube, and this is all stainless, so this is really what we're talking about. It's primarily applying to all stainless steel connections. When I tighten that into a receiving port, because it's a stainless steel ferrule on a stainless steel tube and I'm compressing the end, it really bites into and almost cold welds into place on the end of the tube, so that you can't pull it off. So you can tell that if you wrench tighten it into a port and then remove it, and then you can pull on the nut as hard as you can, and it's almost impossible to get that ferrule off the tube because it's been locked into place. That process is called swaging. Now, reusable fittings don't do that. Reusable fittings are typically made of materials or are engineered in a way that they compress the tube when they're under compression, but then relax and release the tube when you release the pressure, when you basically rotate it counterclockwise to remove it from a port. And that's the advantage of a reusable fitting, because it's not permanently locking into place on the tube. I can adjust that tubing depth to whatever my receiving port needs.
Thanks, John. If any of you in the audience have additional questions, you can email our expert, John Batts, at customerservice.hs@idexcorp.com. In a moment, you'll all see a survey on your screen, and we hope you'll answer that to give us your feedback. For LCGC and IDEX Health and Science, I'm Laura Bush. Thank you very much.